All right. Hey, there was a couple days. You probably wondered where I disappeared to. I didn't disappear, but here we go. I hope you got this problem. So you've had plenty of time to work on it. Let me go over how to do it. It's the kind of problem I like because it tests a lot of your different skills to make sure that you've got them and that you've got them under control. So take a look at this problem, and of course, what's the first thing you should do? And if you've never done this before, I hope you realize I've been saying these things over and over again because I'd like to get them ingrained in you. If you don't know what to do something, even if you don't know why. I mean, I know maybe that keeps on sounding crazy, but it's better to try something than to just stare at it blankly forever. So I look at it and I think, what's the most annoying or disturbing thing about it? And it's probably these square roots. So how do we get rid of a square root? Well, we square both sides. But we got to be careful. We're going to square both sides. The right-hand side squares nicely. Remember, squares and square roots, they undo each other. No problems there. I'll give myself a little more room here. 2x plus 3. But what I've got here is a special product. We've got a plus b squared. We've got something plus something all squared. That's our special product. Here, let me just write it down. I know I've written this down many times, but let me just write it down temporarily before. If you've got a plus b and you square it, right, you get a squared plus, 2ab plus b squared. Well, that's what we've got here. The first thing squared plus 2 times this plus this squared. And this is not going to look nice when I write this down. And if it's the first time you're doing this, this can be extremely disturbing to the point where you'll want to quit. I'm not saying you wanted to quit, but I've seen it a lot where, here, let me write it down. This thing squared, that's easy, 3x minus 1, so maybe no problem there. But plus 2 times this times this. Well, the first 2 times this would give you 4, but then this. And that's what's maybe disturbing. I mean, since I've done 10,000 of these, I'm not disturbed. But if it was the first time I ever did it, yeah, I probably would be. And then plus this squared. Yeah, 2x plus 3. That's easy. Okay, so you say, well, it failed. Not completely. We had 2 square root terms. Now we just have 1. So I would say that's a step in the right direction. If you don't know what to do something. What's one thing you can always try doing? Remember, you can always try doing the distributive rule. You could try factoring. You could try adding like terms. We're building up this list of things you can always try. Well, let's try adding like terms. Without a doubt here, we've got -1 plus 4. That would give me 3. Wow, we're about to catch a really lucky break. I didn't mean this to happen. And it's pretty nice. You know, you can't rely on this happening, but I'll take it right now. -1 plus 4 is 3. 3. Subtract 3 from both sides. This 3 would be gone, and that 3 is gone. So we'd be left with 3x plus 4 times the square root of 3x minus 1 equals 2x. Now, normally I wouldn't expect that to happen. Let's subtract 3x from both sides. That seems like a reasonable thing to do. In general, I would expect to have another number over here, like say -x plus or minus some number. That won't affect the way I do the problem. That'll make this just a little bit easier, because now what am I going to do? I'm going to square both sides. I'm going to square both sides again. So yes, we squared both sides, and then yes, we're going to need to square both sides again. So let's square both sides again. One of our rules of exponents, remember one of our rules of exponents looks like this. If you have star times w and you square it, you can square each one separately. Now, remember what I said, the rules of exponents are a lot like tools in the toolkit. You never know when you're going to need them, and you're probably not going to use all the tools on any one particular job you're doing, but it's nice to have them there. So you have screwdriver, pliers, saw, wrench, hammer, what have you. So I need this property right now. When I square this right here, I get this. Well, now we've got a pretty much straightforward. Oh, didn't I just say square both sides? Look what I just did. This is great. I couldn't have planned this. Square both sides, and I didn't square this. But if you square that, you get that. Now, what kind of equation is this? Hopefully you recognize now it's a quadratic equation. Let's multiply this out. 48x minus 16 equals x squared. Now, that is a quadratic equation. Do we know how to solve quadratic equations? Absolutely. That's important to realize. If I said you need to go from here and you need to walk down the street half a mile, could you do it? The answer is almost certainly yes. But that doesn't mean you want to. I understand that. So can you do this? Yes. Do you want to do it? I get it. That's a different issue altogether. But let's go ahead and do it. Now, when I said it's a different issue altogether, it's a different issue altogether because one thing that can happen is the numbers can turn unpleasant. And I can see here that they might turn unpleasant right now. But I'm going to finish this problem. We have to be brave. We have to be courageous, whatever word you want to use. We have to employ grit. I guess that's a fashionable word these days. Here we have x squared minus 48x. Wishful thinking, it was 4x. 48x, let's see, plus 16 equals 0. That's a classic, straightforward quadratic equation. Let's complete the square. Step 1, get the plane number over on that side. That's easy. Step 2, divide both sides by the coefficient of x squared. That's 1. That's great. Now comes the, I want to say the entertaining part. I'm not sure that's really the right word here, but we take this number, divide by 2, that's 24, and square it, and add that to both sides. Now, what I mean by either entertaining or absolutely not entertaining is, here, I'll write this down like this. If you were not in a math class, just somewhere else, and someone said, I'll give you $100 if you multiply 24 times 24. Would you do it? And I'm sure you would. And even if they said, hey, I don't care if you do it in your head or on paper or even use a calculator. I don't care how you do that. As long as you get that done, I'm sure you'd accept the challenge and I'm sure you would collect $100. But I've seen people defeated on problems like this because their brain is tired. I get it. We've already done all these steps to get to here. So you may not have a lot of brain power left. If worse comes to worse, just bust out a calculator. I don't know what 24 times 24 is. I can tell you if I was to think this over in my head, I think I mentioned this before, I would probably use this trick. Look, just use a calculator. But or just write it old-fashioned style, on paper. You can think of it as a special product. See, it's 20 squared plus 2 times 4 times 20 plus 4 squared. See, that's 400. No problems. This is 8 times 20, which is 160, and that's 16. So it's, what, 576? And that may seem like a terrible number, but it's really not. It's just a number. And now we'll continue on. We'll factor this. Now, you might think, well, this is terrible. What the heck? What's the square root of 576? You could use a calculator. However, due to the fact we have some sort of short-term memory, hopefully, I just did 24 times 24 to get 576, so I know that this is 24. So that wasn't too bad. I don't think that's too bad either. So 5, you don't know, but I almost wrote down the wrong number. 560, let's square root both sides. So x plus 24 equals plus or minus the square root of 560. You may want to try to mess around with the square root of 560, but for right now, just leave it alone because that's perfectly correct as it's written. So x equals negative 24 plus or minus the square root of 560. And those are the solutions. There are two solutions. Whether or not you find these answers, these numbers disturbing or not, that's up to you. After a while, you get used to it. Little technical note. This is correct. This is absolutely correct. 100% correct. However, if this was a standardized test, say an SAT or a college placement exam, or if you type this into your calculator, that's not what it would read. So let me go over that just to avoid confusion. Or you look in the back of a textbook or an example in any textbook, it would not leave the problem like that. So here, let me erase this. You can always review the video to go back there. But I don't have a problem if you type that into a calculator and you'll get what I'm about to show you. I mean, I don't know off the top of my head, but 560, I have to think, what are the perfect squares that go into this? And 4 goes into this, and I have to think about how many times. 140? I might want to double check that. 4 times 100 is 400, and 4 times 40 is 60. Yeah, okay. So the square root of 560 is equal to the square root of 4 times 140, which is equal to 2 times the square root of 140. Now I have to think, are there any perfect squares that go in 140? Wow, I think 4 goes to 140. Yeah, so we could continue here. Let's just continue on this way. This is 4 times what? 35. Oh, double check me on that. Make sure I haven't made any careless errors here. So square root of 4 is 2. 2 times 2 is 4. So this is 4 times the square root of 35. 35 is 5 times 7. Those are both prime numbers. They're not perfect squares. Nothing to do with it. So if you were to type this into a calculator, this is what you would see displayed. Or I mean, just square root of 560. Frankly, you can type in quadratic equations and you will see what I'm about to write down. This. If you straight away see a decimal A, that's not even correct, although it's close, but it's not correct. And B, it tells you that you have a very outdated, old calculator. Because if you have a newer style calculator, this is what you would see. You wouldn't see this, you would see this. Notice there's no real advantage to this. There used to be an advantage in the olden times, in the very, very, very olden times, when you didn't have calculators. And I have to admit, by the time I hit high school, there were handheld calculators. There weren't prior to that. I was right at the threshold. In 7th grade, my junior high school, my middle school, bought an amazing thing. They bought 4 calculators. I won't even tell you what year this was in. They were so proud, and they probably cost like $1,000 each, and they could add, subtract, divide, and multiply, and that was it. And I remember in my math class, we took a field trip down to the calculator room to see these amazing electronic devices. They were about the size of a textbook. They could add, subtract, divide, and multiply, and I think they cost $1,000. And that was many moons ago, as they say. So at any rate, hey, that was probably, when would have that been? I don't know, I saw the first calculator, the first time I ever saw a calculator in my life, I think was 1972, 73, in Sears. So I don't think they're even in business anymore. And it was the same kind of calculator, but $1,000. And there was a line of people waiting to use this modern device. No one had ever seen such a thing as this electronic device, and it could add, subtract, divide, and multiply. Amazing, and even just a few years later than that, by 76, 77, you could buy a fairly reasonable calculator for a fairly reasonable price. So I missed out on this. But if I was just a few years older, what I would have done is when I confronted these, I would have looked them up in the back of a textbook, or use something called a slide rule. If you're ever up at Mesa College, I think that in a display case of sort of ancient computing devices, there's a picture of a slide rule, or an actual slide rule. And but when you look these up in a textbook, you probably couldn't have found this number because the table didn't go that far, but it went up to square root of 35. So you could look this up and then multiply it by 4, and then you could go about your business. That's all a thing of the past. So when I go from here to here, that didn't give me any benefit. Now, if this had been divided by, let's say, some sort of an even number, then I could have had some simplifying going on, and then there would have been an advantage to that. But in this case, it wasn't. Okay, now I want to show you one other, or two other, actually, quadratic type equations. Quadratic type equations, and here's one. Let's say we have, I don't know how difficult I want to make this. There's no particular reason to make it super difficult now, but x to the 4th, let's say minus 3x squared minus 4 equals 0. Is that a quadratic equation? No, because it's got an x to the 4th. It's called the quartic equation. Is there a general way to solve quartic equations? Yes, but whoa, we are not going to get involved in that at all. That was basically, when that's a 3 and a 4 is basically discovered, depending on which historical account you believe, by a guy named Cardano in Italy in the 1500s, but it's complicated, like really actually pretty complicated. So we're not going to do it. But just look at this for a second. Just close your eyes, then look at it real quick. For a second, you might think it's quadratic. It kind of is. It isn't technically, but it's a quadratic in disguise. Watch what I'm going to do. Well, that's not very useful. Now I'm gonna, I don't have to, look, I'm gonna do something right now that most people do. You don't have to do it, but I'm gonna do it anyways. Pick a letter, any letter. I don't care, just not X. Any letter. I'm listening to suggestions. See, I don't care what letter, I don't care what symbol. I'll pick the letter U. If you ever make it to calculus, you'll see why this is kind of a traditional choice, but you don't have to use U. You could use A, you could use T, you could use alpha, beta, make up your own symbol. It doesn't matter. But I'm going to say let U equal x squared. And then when I do that, watch what's going to happen when I make this substitution, usually affectionately known as a U substitution. But here, we get U squared. See, I put U in for x squared, minus 3U minus 4 equals 0. And then you say, hey, amazing. That's a quadratic equation. And I know how to solve those. We could complete the square, but this one's factorable. So if you can factor it, and most of them don't, but if you can, take advantage of that fact. It's like a gift somebody gave you. So here, U minus 4 and U plus 1 equals 0. So U minus 4, our zero product our zero factor, what the heck did we call it? Because I don't want to call it anything. If you multiply two things together and get 0, at least one of them's got to be 0. Zero factor property, maybe 0. I don't know what it's called. Who cares? Sometimes I care. Like, you need to know that's a quadratic equation. That's the term I care about. You need to know what completing the square is. I care about that. You need to know what it means to factor something. I care about that. But if you multiply two things together and you get 0, who cares what you call that? It doesn't really matter. U plus 1 equals 0. So look at this right here. We get U equals 4 or U equals negative 1. We're done. Wait a minute. No, we're not. We weren't trying to solve for U all the way along. We were trying to solve for X. So what was U? U is x squared. So x squared equals 4 or x squared equals negative 1. Square root both sides. If you square both sides here, you get, let's see if this can be seen here. It's right over here. You get x equals plus or minus 2, or we also get some additional solutions. X equals plus or minus the square root of negative 1. And here's a case where you do always have to ask the following question. You do. Are we playing with complex numbers or not? Now, it's my job to say either yes or no to that. For those of you that move on in math, you'll see sometimes you will be playing with complex numbers, and sometimes you won't. If you're not playing with complex numbers, then the answer here is just that. This wouldn't make any sense if we're not using complex numbers. Hey, just like any modern calculator, you can put it in one of two modes. You can put it in the mode that says we're not dealing with complex, or imaginary numbers, or we are. But if we are, then we would take the square root of negative 1, and that's this. And that means there are 4, yes, count them, 4 solutions for this equation. And you can put them in there and they check out pretty easily. Hey, let me just check it out for I. Maybe you've never done such a wild and crazy thing as that. Let's put I into the original equation and see if it actually works. Again, you can put 2 in there. 2 to the 4th is what? 16. And then 2 squared is 4, 12. 16 minus 12 is 4. 4 minus 4 is 0. Fine, checks out. Let's put an I in there. I to the 4th minus 3 times I squared minus 4 equals 0. What's I to the 4th? Well, here, let me go ahead and write it out. I times I times I times I minus what's I squared? By definition, that's negative 1. Remember? That's what I is. We just flat out declare that I is the square root of negative 1. So by definition, I squared is negative 1. Here, I love to leave it as minus 4 equals 0. Well, look, I times I, negative 1. I times I, negative 1. Negative 1 times negative 1, 1. Here. lo and behold, it checks out. So yeah, this all, it works. Amazing. So this is sort of what I think of as this kind of equation here. It doesn't per se have a, what did I just drop? A cap. If I don't find it, it's going to dry up. Since each one of these is a disaster strike. Hey, this is an amusing use of your time on YouTube, huh? Oh well, that marker, my blue marker is dead. I'll substitute this. Okay. To me, these are quadratic equations in disguise. They're quadratic-esque, or I don't know which one to call them. Like I said, they don't have an official. Well, it's a fourth order equation, but it's a jump. Hey, look at this right here. You see that equation? We're not going to touch that. This kind of equation I mentioned. Remember, I went over the history of this before. But this kind of equation, make that a 3 or a 4. That stumped mathematicians around the world for about 3,000, a little over 3 from around 1700 BC when the Babylonians first proposed it, till the early 1500s AD. So what would that be? 3,200 years, probably plus or minus a century. On the 1700 part, I mean, we know when this was solved. Basically, there's some intrigue and maybe somebody stole it from somebody, but essentially, I think it's attributed to a guy named Cardano in Italy. But again, there was actually somebody hired a hitman to go after somebody else, accusing they stole it, and there's this interesting history. Mathematics was sort of like a sport in Italy in the 1500s. One town would challenge another town with their mathematicians. So I guess there was glory and fame, and who knows? I don't actually know if there's money at stake, but there might have been. So you can look up more on that. If you Google solution of cubic equation, I'm sure you get the whole history, and it's actually kind of interesting. Believe it or not, history of math. Who would think? One more like this. Let's suppose we have this. Gotta get rid of some bad markers, huh? I hate to part with markers, but x to the power of 6 minus 3x cubed minus 4 equals 0. Now notice it seems pretty similar to the last one, and in fact, yeah, it is similar to the last one. So I'll use a different letter this time. Let's see, let a equal x cubed. Now it's always going to be that middle chunk. This is not a lucky break that this is this squared. Not a lucky break. If it wasn't that way, we'd really be stuck. Actually, for example, if you make this just an x, you really are stuck. It took another almost 300 years, but in the early 1800s, in particular, somebody named Abel and somebody named Galois proved that if this is greater than 4, there is a solution, but you can't find it. So I'll leave that alone for now. If we were in calculus, we would talk a little bit more about it. Or if you want to Google solution of higher order polynomial equations, you can find, or quintic equation, that's a 5. You can find out all you want to know. It's remarkable that someone proved that you can't do something. It's not that you're not smart enough, not that you're not clever enough. He proved that it can't be done. But we can do this because when I make the substitution, we're going to get a squared minus 3a minus 4. Now that's the same equation we had a second ago, so I factor this, set the factors equal 0, and we wound up with a equals 4 or a equals -1. But what was a is x cubed. X cubed equals -1. Let's cube root both sides. And remember, when it comes to roots, if it's not nice, it is what it is. And I know I feel like that's an emotional thing, because this is really, honestly, I'm not making this up. It's the cube root of 4. It's the cube root of 4. This is really, really, really what it is. Now, if you have a more advanced calculator and you type in the cube root of 4, that's what it will say right on the screen, right in front of you. Really. Then people believe it. I know they won't believe me, but they'll believe when they see it on a calculator. Like, oh, okay. Now, what's the cube root of -1? That's kind of nice. It's -1, because -1 times -1 times -1, -1 times -1 is +1 times -1 is -1. So, yep. So there's the solution. Now, before we sign out here, that's about it for this particular video. But Let me see. Let me tell you where we're headed next. So this is from. Let me write this down. Where is it? Oh yeah. I know what we got to do next. You betcha. Yeah, this is all from chapter 9. And what we're going to do next is, well, I haven't done any word problems. I haven't done any so-called application problems. And we haven't graphed these. So what we're going to do next is, I don't mean to make it sound like, oh, this is going to be terrible or horrible or anything like that, because I don't think it is. But I think what we'll do next is we'll do graphing. Graphing of quadratics. So in the next video, we will do graphing of quadratics, and that appears to be 9.6 and 9.7. And then 9.6 is, what is it, 9.6? Sorry, 9.5 is applications. What I was doing here today, I know I mentioned before, but this is 9.4. So all this stuff here is 9.4. We'll do graphing next, and then I'll think we're going to do a couple of specific word type problems, but maybe not all the types in the book. So in the next video, we'll do graphing, and then we'll talk about, so-called word problems or application problems, which ones I want you to know how to do. But graphing, yes, we're absolutely going to do that. And the graphing is, I didn't write it down, I said it, but the graphing is 9.6 and 9.7. So we'll do all of this in the next video, and then some of this. Okay, all right. That's enough for this video, I think.